Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 12. In last session we were discussing about the terminology called lift, that's what is application to your compressor and turbine aerofoils, and we have realized this is what is a main driving for our compressors and turbines. So, we were discussing about the lifting force, how we are utilizing the lifting force and how we will be having the rotation of our wheel or rotation of our rotor. Mainly for compressor, as we have discussed, my rotation will be from suction side to the pressure side, and for turbine we will be having our rotation from pressure side to the suction side, and that is what will be giving us the benefit in sense of using our lifting force. Then we have discussed about the flow over aerofoil. We have realized how the flow, that is what will be moving from leading edge to the maximum thickness, and then after from maximum thickness towards the trailing edge. So, initially we have discussed we will be having our flow to be laminar flow. After maximum thickness up to some distance we will be having the flow transition, that is what is happening, and towards the trailing edge we will see our flow to be more turbulent. So, those who are having the background of fluid mechanics or having the background of aerodynamics, just go through these terminologies called laminar flow, transition flow and your turbulent flow. Okay. Then we were started discussing about different kinds of aerofoils which we are using for our axial flow compressors and fans. So, if you recall, we were discussing about the C4 aerofoil, we were discussing about NACA 65 aerofoil, we have discussed about say computationally made say controlled diffusion aerofoil, we have discussed about double circular arc aerofoil, we have discussed about multiple circular arc aerofoil, we have discussed S type of aerofoil. And as I told, lot of work, lot of research work, lot of development activities, that is what is going on for development of such aerofoils, application to fans, application to compressor, for aero engines as well as for land based power plants. Okay. Now, let us move ahead. Here this is what is one of the feature, that is what was given by Gostello. He has reported whole lot of work related to cascade study, and his data, that is what is available in open literature as on today people they are using. According to him, some of the physical features and unresolved issues in the flow over compressor and turbine blades, that is what he has listed here. And if you recall, I was telling you we are more interested what is happening on our suction surface. And here if you look at, this is what it says: potential interaction, shock structure, combination tone, inlet distortion, incident force vortices. You can see when we are discussing or we discuss about say transonic compressor or transonic aerofoils, we will be having formation of shock near the trailing edge. And as we have discussed, this trailing edge, this leading edge, that need to be a sharp leading edge. Okay. If it is a sharp leading edge, then only we will be holding our shock on the surface of my blade. Next, if you look at, that is what is say the noise issue, that is what we are defining in sense of say combination of tone. So, when my wheel, that is what is rotating, or my rotor it is rotating, it will be cutting the air, and that is what will be giving the generation of noise. So, majority of contribution of noise, that is what is coming from the rotation of my wheel. We are having inlet distortion. You can realize this distortion is nothing but it is a disturbance. This disturbance maybe we can say in sense of pressure, in sense of velocity, in sense of total pressure, say in sense of total temperature, or maybe because of atmospheric change, or say because of your cyclone. All those things, that is what will give my flow at the entry to be disturbed, or it is different from what it is been designed. So, that is very challenging aspect. These days universities and industries, they are working on development of this kind of fans and aerofoil, which are called distortion free fans, or say distortion free compressors. Okay. Then we are having say leading edge bubble, laminar layer, we will be having buffeting, we will be having say roughness. You can understand when we are flying. So, along with your air, there may be possibility that dust particle also will get sucked from say atmosphere, and that will be sticking on the surface of my blade. And you can understand we are looking for our surface of this suction surface, that to be a perfect surface. Other than this suction surface, if I will be having sticking of air say particle, dust particle on this surface, that will change my flow physics on the suction surface, and that is what will give off design performance. Means for what we have designed, that compressor will not work according to our expectation, and that is the reason people they are doing after few flying hours, they are doing compressor washing. Okay. Then we are having say distributed roughness, transition region, incident wake, calm region, laminar separation bubble, stall behavior, turbulent separation, acoustic propagation. Along with that, we are having say heat transfer, we are having tender blading, we are having cavitation. Suppose say I am using this kind of aerofoil for say my axial flow pump, there I am having problem, that is what we can say, it is a cavitation problem. We are having flutter, it is your aeromechanical problem, shock boundary layer interaction, shock curvature, jet impingement, film cooling, vortex reading, so many. So, you can understand all these aspects, that is what need to be considered when we are making aerofoil, and that aerofoil which is application to your compressor, which is working under adverse pressure gradient. So, just look at the challenges what we need to face when we say we are using our aerofoil for making of blade. It is not that easy in that sense. Even on my pressure surface, I will be having boundary layer thickness and radius of say concave surface, that is what will be giving you Gottler vorticity on that surface. Okay. So, just realize what we mean to say is, your aerofoil what we will be using for axial flow fan or say axial flow compressor, it is having so many difficulties, as on so many issues people they are still resolving. Okay. Now, with this background, let us try to move ahead, let us try to understand how this is what will be helping us for say design of our compressors and fans. So, here if you look at, this is what we say, we have arranged our two aerofoils at particular section, say at mid section. If I am arranging in this way, that is what is called linear cascade. We will be discussing what is the meaning of that. At this moment, just realize I have arranged these two aerofoils as per my section at particular station. This region, as we have discussed, it is called my leading edge and trailing edge. We are having inlet area, outlet area. Suppose if I consider my entry velocity is V1, I will be having my exit velocity say V2. Okay. The distance between these two aerofoils or two blades, people they are defining that as a pitch. Okay. If I will be measuring my distance from leading edge to the trailing edge, that is what is defined as a chord, and if I will be measuring my distance vertically, that is what is called axial chord. We will discuss again when we will be discussing about the aerodynamics of these blades. Okay. Now, here if you look at, this is what is a plot from NASA SP36. So, you can see here what it says, as we have discussed, somewhere here I will be having my stagnation point. We will be having our acceleration of flow, that is what is happening on my suction surface. So, you can say this is what is representing my acceleration of flow. You can see whole lot of acceleration, that is what is happening on my suction surface. Okay. You can say around 10 to 15% of chord you will be having maximum velocity. So, here I am writing that as a V max. Okay. Now, what is happening when we are moving downside, as we have discussed, this is what is your diffusing passage, and for diffusing passage we will be having our flow, that is what will be getting decelerated. So, here if you look at from this 15% chord to downside, my velocity, that is what is decreasing, that will lead up to say my trailing edge. Okay. In line to that, let us see what is happening on our pressure surface. So, here if you look at for pressure surface, we will be having initial acceleration. You can see in this particular region we will be having the acceleration of my flow, and then after it will be having the deceleration of flow on my pressure surface. Okay. So, too much of acceleration, that is what is happening on my suction surface. We will be having small acceleration, that is what is happening on my pressure surface. Okay. And this together if you will be joining, that is what is representing what is happening with my velocity on the surface of my aerofoil. Okay. Now, here if you look at, this is what is representing my pressure coefficient versus my chord. Okay. This is what is representing my leading edge, and this station, that is what is representing my trailing edge. Okay. And we have seen in last lecture, we are having say subsonic aerofoils, we can say it is a C4 aerofoil, we are having NACA 65, we are having or 65 series, and we are having double circular arc. And here if you look at, this is what is representing the actual shape of your aerofoils. Okay. So, if we compare in that sense, we are looking at, say if you look at my C4 aerofoil, that is what is this dotted line, it says I will be having larger leading edge, and that will be having maximum thickness up to some station. It says this is what is the station where I will be having my maximum thickness. If we look at the next, that is what is say NACA 65, that is what will be having my leading edge shape, that is what is different, and my suction surface and pressure surface, say initial stage up to maximum thickness, I will be having that to be lower thickness compared to my C4 aerofoil. And if you look at for DCA double circular arc, you can see the leading edge is almost say it is a sharp edge kind of configuration. It will be having small radius at the leading edge, it will be having small radius at the trailing edge. So, this is what is representing my DCA aerofoil. Now, if we will be measuring what is happening on my suction surface and what is happening on my pressure surface, that is what we will be representing in sense of the term, that is what is called say pressure coefficient. So, this pressure coefficient is nothing but the pressure we are measuring on the surface minus free stream pressure by half rho v square. So, those who are having the background of aerodynamics, they may be knowing this is what is representing my pressure coefficient. Now, this pressure coefficient in your experimentation for aerodynamics lab, you might have measured this pressure distribution, and then after based on that you might have calculated your lifting force. Okay. Now, let me tell you, we are also in line to that only. Only difference is what we are understanding for aerofoil in aerodynamics, it is for wing, and here we are talking about aerofoil at particular station. Okay. Now, have a look at what is happening in sense of your pressure coefficient. So, first let us look at say what is happening on my C4 aerofoil. So, here this is what is representing my suction surface. So, what is our observation? I will be having whole lot of acceleration, that is what will be happening on my say suction surface. So, when I say acceleration, that is what is happening, my Cp value, that is what will be decreasing. So, you can see this is what is representing my say acceleration of flow on C4 aerofoil. Then after it will be having say deceleration of flow, that is what is moving downside towards the trailing edge. So, you can see this is what is representing the acceleration of my flow for C4 aerofoil. If we look at on pressure surface, again on pressure surface we will be having the acceleration of flow, that is what is happening on say pressure surface. So, here if you look at, this is what is representing the acceleration of flow near the leading edge. Okay. And then after slowly I will be having the pressure rise, and that is what will be merging near my trailing edge. So, you can say this is what is representing my CP distribution. Let me tell you, area under this curve, that is what is defined as a lifting force when we are saying aerodynamics. If we are using this concept for our compressor aerofoil, basically area under this curve, that is what is representing my pressure rising capacity of that particular aerofoil. Okay. So, when you are doing your design, after doing design, maybe you will be going with say your computational study. In computational study, it is preferred that you understand what is happening with your CP distribution on your suction surface and pressure surface at particular station, and just look at how you are managing your flow on suction surface, how you are managing your flow on the pressure surface. You can understand if I will be managing my flow nicely on my pressure and suction surface, that is what will be giving me very good CP distribution. That means, it will be giving me what pressure rise I am expecting. Okay. So, many times people when they are doing their computational study, they need to do post processing in sense of understanding what is happening at particular station. So, they are using this CP as one of the parameter. Let me go to the next. This is what is representing for say 65. So, this is what is for NACA 65. Here also I will be having my acceleration of flow, that is what is happening, but in compared to your C4, my acceleration is slightly lower on the suction surface. Same way this acceleration, that is what is happening, slightly lower on my say pressure surface also. And here if you look at, this is what is representing my distribution of CP for NACA 65. Okay. And as we have discussed, for double circular arc, I will be having acceleration, and that acceleration will be moving towards the downside here. Okay. So, if you compare for say my C4, that is what will be around say maybe 10 to 15% of chord. For NACA 65, it will be from 15 to 20%, and here if you look at for double circular arc, it will be around say 40% of chord, 30% of chord, you will be having say acceleration of flow, and then after you will be having smooth deceleration of the flow. If you look at carefully and if you are comparing all together, you will see my pressure distribution on the pressure surface for double circular arc, that is what is roughly constant. Okay. So, this is what will give us idea what is happening in sense of my CP distribution, and now we realize what is the use of my lifting force when we are talking for application of say your compressors as well as fans. Now, you will be going aggressive. We are always discussing we want to increase the pressurizing capacity of particular stage. That is what is in order to meet lot of requirements, lot of expectations for future engines, and if you will be going aggressive, then there may be chances of flow separation, that is what will be happening. And when I say there is a flow separation, that is what will be happening, it will not give what CP distribution we are looking for. So, when I will be discussing about the cascade, that time we will be discussing these aspects, what is happening there. Now, with this data, say Americans mainly for NASA, earlier named as NACA, they have come up with some solution say in sense of diffusing capacity of particular aerofoil or for particular rotor and stator configuration. What they say, like if I consider this is what is say my maximum velocity, if I consider I am having my entry velocity is V1 and my exit velocity is say V2, then they say they have introduced the parameter, that is what is called say diffusion factor. So, what it says, based on say velocity gradient on the suction surface, they have defined this as say V maximum. So, this is what is my V maximum. Here this is what is my V2. So, here you can say it is a V2. So, it is V maximum minus V2 divided by V1. Okay. Then slowly they realize, rather using this relation, this is what is depending on aerodynamics of my arrangement. So, this is what is they are saying, say here S, that is what is representing my pitch. So, you know how far I have placed my blades, okay, or how many blades I have accommodated in particular distance, that is what is called my pitch, and what is my chord. Okay. Then they have replaced this with delta CW, and they say my diffusion factor, that is what is a function of say my relative velocity or velocity at the exit, velocity at the entry, what is my delta CW, that is what is my working capacity, delta CW, that means CW2 minus CW1, and this is what is depending on my parameter called pitch, and it is also depending on my chord. Okay. So, this if I am using V, that means we must realize this is what is in relation with our rotor. Okay. For rotor we are interested in relative velocity. Okay. And just recall, for rotor our relative velocity at the entry, that will be larger, my relative velocity at the exit is lower. Okay. Suppose say if I am using this concept for the stator, for stator also we can do the calculation for the diffusion factor, but in that, in place of using your say relative velocity component, we need to go with the absolute velocity component. So, this is what is the relation for that. Okay. So, based on say understanding what is happening on the surface of aerofoil, they have come up with the solution, that is what is saying say diffusion factor. Let us see how exactly we will be using this parameter called diffusion factor. So, this is what we know, my diffusion factor, that is what is maximum velocity minus say exit velocity divided by entry velocity. If I will be replacing my velocity component, say relative velocity component, and my relative velocity component at the entry and exit, I can write down in sense of my beta 1 and beta 2. So, using your velocity triangle, we will come up with say diffusion factor, that is given by 1 minus cos beta 1 divided by cos beta 2 plus cos beta 1 by 2 sigma and tan beta 1 minus tan beta 2. Now, here this sigma, that is what is defined as a solidity. Okay. So, in sense of understanding now, let me introduce one more parameter, that is what is called solidity. This solidity basically it is defined as say chord to pitch ratio. When I say pitch, I will say this is what is given by 2 pi r by z. So, you must realize, suppose say this is what is say my rotor. So, at all stations, at all radius, at all diameter, I will be having this solidity to be different. Okay. What we were discussing in earlier case, this is what is at particular station. Now, like we have realized our blade, it is made up of say number of aerofoils, it has number of stations, and this is what is having 3-dimensional shape. So, you can say for all the stations you will be having different solidities. Same way at all the stations you are having different beta 1, beta 2, okay, because my peripheral speed is changing, though my axial velocity is constant. So, I will be having variation of my diffusion factor all the way from hub to shroud or hub to tip. Okay. So, this is what is the compilation of data, that is what was proposed by say NASA. So, in NASA SP36, they have plotted this, and they say this is what is representing my diffusion factor, and this is what is say my frictional losses. So, basically they have correlated the separation process or say losses in sense of friction losses. So, what they say, like for say rotor hub and stator, my frictional losses, that is what is remains almost constant. Okay. And if I am talking about say diffusion factor, that is what is moving from 0.4 onwards, if you look at carefully, then near the tip region my losses, that's what will be going to increase. Okay. So, my losses, that's what is going to increase. Okay. So, it says this logic or this plot, what we are saying in sense of diffusion factor, that's what is applicable for say subsonic or high subsonic kind of aerofoils. As per NASA, this diffusion factor should be less than 0.6. If you are going more than 0.6, you can understand you are increasing your losses. And when I say you are increasing your losses, your efficiency will go down. Okay. So, for most modern design, people they are assuming this diffusion factor in the range of 0.5 or less than 0.5, okay, to be on the safer side. Okay. Now, for stator also they are putting this diffusion factor in the range of 0.5. So, now just realize we are now moving towards what all calculation we need to do for design. So, this is what is one of the important parameter when you are doing your design of axial flow compressor. Okay. So, this is what is defined as my diffusion factor. Okay. Now, here if you look at, this is what we have discussed in sense of diffusion factor, and we have defined this sigma as my solidity. So, solidity we have defined as a 2 pi r by z, that is what is representing at different radius for particular number of blades. So, z is nothing but my number of blades. Okay. So, here this is what is a presentation for, you can say it is a low aspect ratio blade. So, it is around say aspect ratio in the range of 1, okay. Aspect ratio in the sense height of the blade to chord of the blade, that ratio is defined as aspect ratio. Same way here on right hand side you can see this is what is a high aspect ratio blade, where your height of the blade or span of the blade is larger and your chord of the blade, that is what is smaller. Okay. Now, this is what is representing what will happen if I will be changing my number of blades. Suppose if I consider this is what is say having 12 number of blades. So, you can say I am making this passage. This particular passage we have realized that is what is your 3-dimensional passage, where your diffusion, that is what will be happening. Okay. Now, if I will be reducing my number of blades, say suppose I am reducing that to 8 number of blades, what will happen? My passage area at the entry and my passage area at the exit will be changing, and my length, that is what is remain same, because I am not changing my chord. So, this is what will be giving you maybe say formation of your stall or separation of your flow from your suction surface, or it may not be giving what pressure rise we are expecting. Okay. So, in order to achieve that particular pressure rise, so diffusion factor, that is what is giving you idea in sense like how much maximum pressure you will be achieving. Okay. So, let me increase the number of blades. Suppose say here I am increasing my number of blades to say 15 number of blades. What will happen? Again here if you look at my passage area, that is what is say reducing, and that is what may give you what you are looking for in sense of pressure rise. Okay. Now, just look at what is happening with my high aspect ratio blades. When I say high aspect ratio blade, I am having my span to be large, or my height of the blade is large and my chord is smaller. Okay. So, if this is what is your case, my diffusing passage you can understand available, that is what will be smaller length. So, it is more challenging in that sense. So, if you are looking here, I am looking for more number of blades, say this is what is say original, or we can say 19 number of blades. If I will be reducing my number of blades, you can say my flow area between these two blades, that is what is going to increase. That may not give what pressure rise we are expecting from that rotor. Okay. Same way if I will be increasing my number of blades here, I will be having my passage area, that is what will be smaller, and if that is what is your case, you may be able to achieve say pressure rise what you are looking for. Okay. But remember one thing, when I say I am increasing my number of blades, we need to pay somewhere. That's what will be in sense of losses, first thing. Secondly, that's what will lead to increase the number of blades on your rotor as well as stator, and that's what will be increasing your weight of the engine. So, people, they are doing the optimization in order to reduce the number of blade. If they are able to reduce one number of blade, that's what will be paying them, say in dollars at the end of the year, it's a huge amount. Okay. And that's where whole development activities, as I say, it is happening. When I say low aspect ratio blade, it is more systematic way of doing the diffusion process. When I am talking about, say, the high aspect ratio blade, since my chord available is very short, though you need to manage whole your diffusion within this particular length only. That's what is more challenging in sense of doing design. Okay. So, just realize the thing, this diffusion factor what we are introduced, what we have talked about, that's what is very important parameter when we are saying for our design. Okay. And this diffusion factor, that's what is the estimation. So, throughout the world, people, they are using this diffusion factor as one of the parameter for checking or assessing the performance of that particular design. Okay. So, this diffusion factor is suggested, it says my diffusion factor that need to be in the range of 0.5. So, many times people, they are assuming this diffusion factor to be 0.5, based on that they are deciding the number of blade. So, that is also one of the design challenge, how you will be deciding the number of blades. So, people, they are using this concept of diffusion factor many times for, say, deciding the number of blades, or maybe in order to increase or decrease the diffusion factor, they are changing the number of blades, they are changing, say, chord length, maybe they are changing the aspect ratio of the blade. So, here we are stopping with. Thank you very much. I hope this has given more clarity to you in sense of design. Thank you.